Alright, hey guys, what's going on? So today we are going to be talking about visualizing the Ricci tensor, and then we're going to get into the Ricci scalar after that, and then from there, like I've mentioned in the previous video, we're going to be stopping on tensors for a little bit, going into some different areas in tensor calculus, and we're also eventually going to be starting, or soon going to be starting, general relativity playlist as well. Happy holidays, and let's get straight into the topic. So today we're visualizing the Ricci tensor. So the Ricci tensor is going to be something that tracks volume changes along a geodesic, or along geodesics. And then the Ricci scalar, which we're going to see later, is going to be something that's going to be able to help us compare the volume of a ball in curved space versus flat space. So the Ricci tensor is going to say, well, as we travel along some geodesic, the volume here is actually going to change. So the volume, as you travel along some geodesic, some object at a point P, right? So say at this point P, we have a sphere, right? So we have this sphere located at point P, and as we travel along the geodesic, the sphere is actually going to decrease in size. And the Ricci tensor is going to tell us something about how that decrease in size is going to work. And the Ricci scalar is going to be, well, suppose we're at point P again. Here's our point P on our manifold, and at that point P, we can also understand something about how areas deviate from flatness. So this is the same circumference as we would see in flat space, but because this is a sphere, this area is actually going to be greater than that, and it'll be less, right? It'll be less if we have something like. So here's our, actually I'll do it like this, right? It would be less if, here's our circle. This is sort of inverted, right? So we have a sense of what is meant by negative and positive Ricci scalar values. But anyways, that's what these things are going to tell us. In this video, we're going to go over the Ricci tensor first, and then we're gonna go into the Ricci scalar, and then we're gonna see how this all ties in with the Einstein tensor, right? So the Einstein tensor, G mu nu, right? That's gonna be made up, we'll find, of the Ricci tensor, right? This is the tensor. And then that's going to be plus 1/2 the Ricci scalar times G mu nu. That's the metric, right? So embedded within this guy is R mu nu alpha beta. That's the curvature. And we get the scalar from this guy, right? So this is all how this is going to work. We're going to understand geometric interpretation of this, and we're also going to our first sort of more advanced tensor that we're going to look at when we finish this guy is going to be the Schouten tensor, right? So the SCHOUTEN, I think is how you say it, the Schouten tensor. This is going to be a generalization of this. We're going to see how this is more of a generalization of this principle right here, and we'll get into that later. Right. So I divert a little bit, but let's talk now about the Ricci tensor. So we're starting off by taking the covariant derivative in the direction v of some vector, right? And we'll see what this vector represents later. But we can we could take the double covariant derivative along what we're going to call separation vector, and we'll see here. We can actually show this right now really quick. So the separation vector is going to be separation between two geodesics. Okay, so that's this S right here. Everything is sort of, I hope everything's color coded. So S is going to be the separation vector. And so we could take the double derivative. We could take the derivative of V in the direction of V, right? So that's going to be this guy right here, taking the derivative in that direction, V. And then, but we can also take the double the derivative with respect to the separation vector as well. So now, so we can add 1 to this, right? So we're adding nothing here, or we're just adding this whole piece. But we find out that this here, well, this is the Ricci, or this is the Riemann curvature, right? That's this. So all of this is right there, and then we're left with this guy right here, which is right here. All right. And then we take this to one side, and we get that this is the geodesic deviation vector, right? So this here is our, if we put, let's see, if we put subscripts on this and superscripts, the two input vectors are going to be alpha beta, say. That's going to be this, say this guy has alpha on it and this guy has beta on it. The two input vectors are these two guys. And then this is going to be a beta, and this is a vector, so we just put an extra contravariant component to it. So this here tells us something. This is a geodesic deviation vector. This looks like a tensor, but when all these vectors are supplied to it, right? The separation vector. This is the separation. This is the direction. This is the vector traveling along that direction, and this is what makes it a vector when everything's fed into it. This is a vector, right? And this is what we're going to call the geodesic deviation vector. Okay. So V, and so this is V, we're taking its derivative along some geodesic, and then we're also taking its derivative with respect to the separation vector. We can notice that the inner product, as we take this derivative, as we go further out in this direction, is actually getting less than 0, right? Because if you recall the inner product between, say, vectors that are close together, that means they're going to have lie very close within line to each other, and that tells us something about the inner product. And so the inner product here is less than 0. The inner product here is greater than 0 for converging geodesics. So for diverging geodesics, this inner product is between these two guys is less than 0, and here it gets greater than 0. Okay, both of them initially start. You could say both of them in these two pictures at least initially start at right angles. They don't necessarily have to, though. Sort of depends on where you start, right? If you started here as opposed to here, say this was the point P. None of this, so this is sort of getting a little bit too into the weeds here, but the point here is that this here, right, so the geodesic deviation vector dotted with the S vector is going to be less than 0. So it can sort of be thought of as an inner product, but we're actually going to think of this more as a cross product, actually. I just want to show how the inner product changes as well. And so let's talk about that. Let's talk about that now, because this dot here, this is going to help us in defining the Ricci tensor. So this is what I mean. So we now define the sectional curvature, and this is going to help us define the Ricci curvature. So at some point P, again, this is our point P, say, some point P. Here's our point P. If we're dealing in the case of diverging geodesics, then we have we can draw the parallelogram that the separation vector has with V. Similarly, we can do that in the converging case also. Right, so P is that point. And when we do that, we get an area, and we use this area to normalize the size of this vector. Right, so this vector is what we defined before. We use this area, which is given by the cross product. If you recall from linear algebra, the area of a parallelogram of two vectors can be defined as the cross product between the two vectors. And that's all given right here. So when we flesh this guy out, we actually get this if S was here. What I'll do here is I'll make this guy blue. We're identifying S in this case as e to the I. That's the separation vector. It's the basis vector now. So we identify that. I'll make these guys blue. This is blue. That's not very good. I'm going to change those to straight up blue. All right. And then I have to change this guy to blue also. E, I, like that. Oh, and then we have to do it up here also, right? So we're just changing S for EI. This is a basis vector, right? So nothing's really changed. We're just identifying it as a basis vector. And the Ricci tensor, this is the Ricci tensor now, we're going to say is defined in terms of the scalar, or in terms of the curvature, or this guy here, the sectional curvature. This is a sectional curvature, so it's defined as the sum of the sectional curvature along different orthogonal slices of geodesics. And here I'll skip really quick to actually, yeah, I'll skip to this page right here. So I'll go back to the other page, but we're really just talking about, that's, say, in the E1 direction, and then these guys here are in the E2 direction. So we're taking the section, each one of these is the sectional curvature as some volume expands, and we're gonna see exactly how this works, how the math here works. So the Ricci tensor is defined as this, where the Einstein sum is implied right here. All right, EI. Sometimes things get erased and I don't notice. But this guy here goes, these two, this is 1, this is 1, this is 0. Because these two guys are orthogonal to one another, so this is 0. And so what we end up doing is we get this, and then from here, this is just nothing, right? Anything over 1 is just that thing. So from there we get to this point. We're putting this in component notation. These don't. So we have I and K. Okay. And then we take the components out, and we leave EJ and EK right here, and then this is where sort of the magic happens, right? So these guys are left out. The I, right? So this I is this I right here, and then this K is this K, and then the two input vectors. These are the two directions again, EI and EJ, EI and EJ. And we can see here that the I's and the I's sum over each other, And so, as we've seen, the definition of the Ricci tensor is a contraction of the Riemann curvature tensor. And so we get this. So the Ricci tensor, Ricci, and these are two input vectors. These are the two directions we go on our manifold, right? So, actually, no, wait. Right, so these two vectors, right, not the two directions. So one of these is going to be the direction we're actually, or the vector we actually are transporting. And then the other one, VK, right, so VK is the one we're transporting. VJ is one of the directions. Okay, my apologies. I think the iPad stopped recording there for a second. Anyways, I just want to erase this really quick. And so we get to this point now where we've defined the Ricci tensor as the sum of the sectional curvatures, right? And we find here the Ricci tensor, and this is in component notation. So we're saying that the Ricci tensor is a sum of the sectional curvatures. So if we take a look at the sectional curvatures, which is what we've seen before, this is the sectional curvature, right? So the sectional curvature is one orthogonal section as we travel in some direction, and then the other orthogonal section as we travel in some direction. And in the case where rkj is greater than 0, that means it's always going to be, each direction is always, or each orthogonal slice is always going to be increasing, and the sectional curvature is always going to be increasing. That is to say that V here, the separation vector, is always increasing. Right, so the separation vector is always increasing. When it's less than 0, the separation is always decreasing, right? So so the volume is actually decreasing. So whenever we have this case at some point P, right, remember we could say that this is at some point P, then we have a volume increase, right? And if it's this case, then the volume tends to want to decrease at that point. All right. And what if it's 0? If it's 0, this is 0. Well, we have increasing on one orthogonal slice and decreasing on another orthogonal slice. And so what actually ends up happening is that the volume is not increasing nor is it decreasing. Volume is actually staying the same. So I'll just, without the pictures, we have rkj, I'll write this out, kj and rkj less than 0, greater than 0, equal to 0. These are the three cases we can come across. And so this corresponds to volume stays the same. In this case, the volume increases. And in this case, the volume decreases. This is all at a point, right? This is all at a point P. So we're standing on some point P on a manifold. So here's our manifold. This is all at because again, the Ricci tensor is a function of space-time. The Ricci tensor is a function of space-time. It has its basis, right? E, K, E, J. Gobbles up two vectors, right? We've seen that already. It gobbles up a separation vector. So this one is, say, the separation vector, and this one is the vector this one is the vector that's being transported, right? Separation vector and the vector that's being transported. And so I'll just call that vector right now. That's a little bit, yeah, that's fine. This is a covariant, or a contravariant, right? Contravariant vector. And so we have, so this is a Ricci tensor, and it exists everywhere in space. So you can imagine making spheres at each point in space-time and asking yourself, okay, what's happening to this sphere? What's happening to the sphere at this point in space-time? Well, we can ask two things, right? What's happening to the volume of the sphere, and what's happening to the area if I was compared to if I was in flat space? And that's what the scalar is going to tell us, right? So just to recap, this tells us something about volume, and then R is going to tell us something about area. Interestingly, when we start talking about the Einstein equation, or the Einstein tensor, that's going to be some combination of the volume and the area times the metric. Right, so in some sense we're adding volume and area, but when we multiply an area by the metric, then somehow that gives us a volume. So what does that tell us about the metric? Well, that's going to be something we're going to get into a little bit later here in this playlist. And so that is what I got for you for right now. Monday, I may or may not post something just because it is Christmas Day. And I wish you all a very Merry Christmas and Happy Holidays. And again, if you like this kind of content, make sure to hit that like and subscribe button. And I will see you guys in the next one.